Climate Science 3. This episode, the lapse rate, or greenhouse gases on steroids. The lapse rate is the gradient of the fall in temperature with altitude. Modelling the lapse rate means constructing a multi-layered greenhouse gas model. The temperature of the upper layer being less than that of the lower layers. The combined effect of these layers with different temperatures is to radiate more infrared back down to Earth than is radiated off into space. This boost in energy radiated back to Earth turbocharges the greenhouse effect like as if it was put on steroids. Before we get too far though, we're going to look at photon absorption by greenhouse gas particles. I have 3 packets of air with differing combinations of density and volume. Packet 1 has a high density of particles, whereas 2 and 3 have a low density. Packets 1 and 2 contain the same number of particles, whereas 3 has half the number. In the diagram, the circles in the packets represent gas particles, the white ones being benign, but the red ones greenhouse gases. The row of black circles at the bottom represents infrared photons. Let's see what happens when the photons try to run the gauntlet. Here we notice that packets 1 and 2 with the same number of particles have absorbed the same number of photons, whereas the one with less particles has absorbed less. In this video we're going to produce a multi-layer model of the atmosphere. The thing to note is that if we keep our gas layers the same thickness, the absorptivity will fall off in the higher, less dense layers. Here we have 2 graphs superimposed showing temperature in red and pressure in blue as a function of height. We can see the various layers of the atmosphere, the thermosphere at the top and the troposphere at the bottom, and how they are defined by temperature. Almost all the water vapour and 3/4 of all the atmosphere is found in the troposphere. Certainly above the troposphere, very little radiation is absorbed. So I'm going to model the troposphere only. I've chopped the troposphere into 3 bands of equal height, each band being just less than 4 kilometres in altitude. Because of the fall in pressure with height, the upper band, I'll call it B3, has air that is much thinner or less dense than B1. Here we have a multi-layer model. From the previous graph I obtained the mid-range temperature for each of the 3 layers. The temperature T1 for band 1 is 276 degrees Kelvin. The squiggly arrows represent the grey body radiation from each layer. The straight red arrows represent the infrared transmitted, that is, not absorbed by the previous layer. The absorptivity of each layer is epsilon 1, 2 and 3 respectively. The downward infrared transmitted through each layer is not shown on this diagram. If we wanted to calculate the power generated or transmitted through each layer, we can see that this would be a nightmare to solve, as each layer has a different and, at this stage, unknown emissivity. When it's all said and done, all models without an infinite number of layers are approximations. A 3-layer model being better than a single-layer model, but there's nothing magical about selecting a model with each layer having the same height or altitude difference. Why not select bands with the same emissivity in each layer? Assuming that the gases in the troposphere are well mixed, that would be achieved by selecting layers with the same number of molecules. Let's consider the following. It's convenient to think of the atmosphere as a column. 50 kilometres up, the pressure is about 1 millibar. 12 kilometres up, the pressure increases to 100 millibars, and at ground level it increases to about 1,000 millibars. So why is this? Here we have a translucent cube sitting on a table. The force exerted by the cube on the table is F2. F2 is equal to the downward force on the top surface F1 plus its weight force mg, mass times gravity. The definition of pressure is force over its cross-sectional area. If the cross-section of the box is A, then by dividing both sides of the force equation by A, we have effectively changed the relationship to one of pressure. So F2 divided by A equals F1 divided by A plus mg divided by A. As shown here, P2 equals P1 plus mass per unit area multiplied by the Earth's gravitational constant. On this graph, the troposphere goes from 1040 millibars of pressure at ground level to 260 millibars of pressure at the top of the troposphere, a range of 780 millibars. Then divided by 3, we get 260 millibars of pressure difference across each band. So band 1 goes from 1040 millibars to 780 millibars, 780 being 1040 minus 260. Band 2 goes from 780 to 520 millibars and B3 from 520 to 260 millibars. Band 3 temperature ranges from minus 56 to minus 23 degrees centigrade. That's an average of minus 40. Here we have our greenhouse multi-layer equimass model of the atmosphere. Now the absorptivity and emissivity is the same for each band of atmosphere. We have a problem that can be solved relatively easily. The values for temperatures T1, T2 and T3 were obtained from our typical atmospheric pressure and temperature graphs. The power leaving the top of the troposphere is 1 minus epsilon all cubed times BP plus 1 minus epsilon all squared times epsilon B1 plus 1 minus epsilon times epsilon B2 plus epsilon B3. Equilibrium is achieved when the energy from the Sun equals the energy radiated leaving the Earth's atmosphere. S in equation 1 is the power from the Sun and has a value of 240 watts per metre squared. In equation 2, the blackbody radiation for each layer is given by Wien's law. Bn equals sigma Tn raised to the power of 4. Substituting the appropriate temperature into the formula for each layer gives us values for B1, B2, B3 and BP. Equation 3 is formed from substituting these values and the value for S back into equation 1. We are left with a third order polynomial with one unknown, epsilon. Since we know that the value for epsilon must lie between 0 and 1, we can solve the equation to any desired accuracy quickly through trial and error. You can't emit or absorb more than 100%. That is 1. I found that the true value for epsilon lies between 0.55 and 0.551. We can now use epsilon equal to 0.55 to complete the energy budget for our model. When I looked at the energy balance of each individual layer, I found a deficit. The values in the circles represent the deficits. What is interesting is that the deficit of each of the three bands, 49, 81 and 3, add together to give 133, which is equal to the excess found in the Earth's surface layer. The budget for energy transported to the atmosphere by means other than infrared radiation has popped out of our diagram. The energy anomalies represented a budget for latent heat, convection and UV absorption. In our last episode we calculated the contribution from latent heat to be 78 watts per metre squared, so that leaves 55 watts per metre squared for convection and UV absorption. We now have the situation where 35 watts per metre squared escapes from the Earth without being absorbed by any of our three bands. From the atmosphere, we now have more energy directed back to Earth than off into space. That is, 205 watts per metre squared goes into space as opposed to 283 watts per metre squared fed back to the Earth. In the single layer model we previously developed, the two values were the same. Conclusion. Our model is no longer close to being maxed out. It is easily able to cope with the 78 watts per metre squared from water evaporation and condensation in the troposphere. There is potential left in the greenhouse tank for further heating if absorptivity of the layers were to increase. Since the deficit in the top layer is only 3 watts per metre squared, this indicates that not much water vapour in this layer is condensing out. And since it's much colder than the other layers, there must be very little water vapour in that layer. Otherwise, it would condense out. Prediction. I'd expect that if I broke the troposphere down into more layers than just 3, the difference between the radiation feedback to that which is radiated off into space would further increase.